Fundamentals of the Special Theory of Relativity. Part 1. Relativistic Effects. The study of the motion of light, in particular, measuring its speed, led to the conclusion that the laws of mechanical motion change significantly at high speeds. As it turns out, many characteristics of a moving system change compared to a stationary state. Specifically, time intervals, lengths, and distances along the direction of motion, as well as mass, change. Moreover, the greater the speed of a body, the greater the changes in these quantities. At ordinary speeds, these changes are completely insignificant. They become significant only at speeds comparable to the speed of light. This is why the existence of these changes was only established by studying a fast-moving object like light. Thus, many quantities considered absolute in classical physics turn out to be relative at high speeds, depending on the speed of motion. The effects that arise at high speeds are called relativistic effects, or effects of the special theory of relativity. A body moving at high speed is called relativistic. Relativistic effects include, in particular, changes in the following physical quantities in a relativistic system. 1. Time intervals. 2. Lengths and distances along the direction of motion. 3. Mass. All of these quantities are absolute in classical mechanics, but relative in relativistic mechanics. The general nature of changes in time and space intervals in a moving system is as follows. Time intervals between events occurring in the system increase, while spatial distances and lengths along the direction of motion, conversely, decrease. Therefore, firstly, all processes in a moving system occur more slowly. This effect is called relativistic time dilation. That is, a moving clock ticks more slowly. Secondly, the distances between all points in the system decrease, and therefore the length of the entire system as a whole decrease. This effect is called relativistic length contraction. Due to the length contraction, the shape of a moving body changes, the body flattens in the direction of its motion. As for the change in mass, it increases for a moving system. This effect is called relativistic mass increase. Note that additional mass is not created out of nothing. To change the speed of a body, a force must be applied to it. Mass increases during the period of force applied to the body, due to the energy of the external force. Note that relativistic effects are only observed when a stationary observer makes measurements of a moving system. If the observer is inside the system, that is, moving with it, he will not observe any effects. The time intervals, lengths, and mass of the system will be exactly the same as if the system were at rest. And the reason for this is clear. In this case, the system is at rest relative to the observer. We also note that if a moving body is considered a point, the effects of time dilation and length contraction will not manifest themselves. Because no processes that could slow down will occur within such a body. And the length of such a body, considered zero, cannot decrease. Consequently, the only observable relativistic effect in the case of a point body will be an increase in its mass. Part 2. Formulas for relativistic effects. Thus, the time intervals, length, and mass of a moving body change. The number of times these quantities increase or decrease is the same for all of these quantities and is equal to the square root of 1 minus the square of the ratio of the body's velocity to the speed of light. That is, the time elapsed between the same events in a moving body will be equal to the time elapsed between them in a stationary body, divided by the square root of 1 minus the square of the ratio of the body's velocity to the speed of light. The length of a moving body will be equal to the length of a stationary body multiplied by the square root of 1 minus the square of the ratio of the body's velocity to the speed of light. and the mass of a moving body will be equal to the mass of a stationary body divided by the square root of 1 minus the square of the ratio of the body's velocity to the speed of light. It follows from the formulas that relativistic effects, while dependent on the body's velocity, are completely independent of the direction of the velocity, that is, its sign, since the velocity is squared in these formulas. Consequently, these effects are exactly the same, regardless of whether the body is moving toward or away from the observer. Part 3. Proper time, proper length, and rest mass. As we see, time intervals, lengths, and distances, as well as the masses of bodies in relativistic physics, unlike in classical physics, no longer have a strictly defined, unchanging value. Therefore, their classical values, that is, their values for a stationary body, began to have a special name. Specifically, the time interval for a stationary body, that is, the readings of a stationary clock, is called the body's proper time. The length of a body at rest is called the body's proper length. And the mass of a stationary body is called its rest mass. Part 4. Relativistic effects from the perspective of a moving body. Because of the relativity of velocity, we can transition to a frame of reference in which the moving body is at rest. In this frame of reference, the body in question will be at rest, and all surrounding bodies will be moving in the opposite direction. Then, from the perspective of the moving body, the effects of time dilation, length contraction, and mass increase will be reversed, that is, the body will observe all these effects in surrounding objects. This means that the body will observe that events in the surrounding world have slowed down, the lengths of surrounding bodies and the distances between them along the direction of motion have decreased, and the masses of all bodies have increased. Mathematically, transitioning to such a frame of reference corresponds to changing the sign of the velocity in the formulas for the time interval, distance, and mass of the moving body. But since velocity is squared in these formulas, changing its sign will have no effect, the formulas will remain the same. Accordingly, all effects will be the same. It's worth noting that due to distance contraction, objects moving toward the body in question will be closer to it than when the body is at rest. Thus, when a body moves toward an object, it's as if that object is also beginning to approach the moving body. Part 5. The twin paradox. An interesting consequence of relativistic time dilation is the so-called twin paradox. Its essence is as follows. In the case of a living organism, time dilation means, among other things, that the aging process in it will slow down, that is, a moving organism will age more slowly. It follows that, for example, if one twin were to travel at very high speed and then return, then due to time dilation during his journey, he would appear to be younger than his brother. However, from the brother's perspective, due to the relativity of speed, he and the rest of the world can be considered to be moving, while the traveling twin is at rest. Then, from this perspective, upon the traveling twin's return, his brother who remained at home should be less old. This contradiction is called the twin paradox. Part 6. The possibility of the existence of absolutely rigid bodies. The effect of relativistic length contraction also has its consequences. In particular, the contraction of the length of moving bodies makes the question of the possibility of the existence of absolutely rigid bodies in relativistic mechanics non-trivial. As is well known, an absolutely rigid body is one in which the distances between its points can be considered constant with reasonable accuracy. However, if a relativistic body accelerates, that is, if its velocity changes over time, then the body's length will also change over time. This means that the distances between its various points will also change. It follows that no accelerated relativistic body can be considered absolutely rigid. However, we note that in the case of rotational motion of a rigid body, the change in the body's linear velocity due to rotation can be neglected, since these changes are always small compared to the speed of light. Their smallness is due to the smallness of the rotational velocity compared to the speed of light. Therefore, changes in the distances between points of the body due to rotation are negligible. Thus, in relativistic mechanics, only a body moving at a constant velocity and/or rotating can be considered an absolutely rigid body. Part 7. Maximum speed of light. As the speed of motion increases, time dilation, length contraction, and mass increase will intensify. Moreover, as the system's velocity approaches the speed of light, it follows from the formulas for the changes in these quantities that their values will tend to infinity or zero. Because, due to the infinite increase in mass, further acceleration of such a body at speeds close to the speed of light would require an infinitely greater force. Bodies with zero mass, for example, light, cannot be accelerated or decelerated at all. As it turns out, such bodies can only move at the speed of light. That is, they cannot be at rest or move at any other speed. It is precisely for these reasons that the speed of light is the maximum possible speed of any body. Moreover, the speed of light is the maximum speed at which interactions between bodies can be transmitted. Note that only elementary particles have zero mass. Photons, carriers of electromagnetic interaction, gravitons, carriers of gravitational interaction, and gluons, carriers of the strong interaction between quarks. Ordinary bodies with zero mass do not exist. The formulas for relativistic effects imply that for bodies moving at the speed of light, not only is their mass zero, all time intervals and lengths are also zero for them. That is, time stands still for such bodies, and their length, at least along the direction of motion, is zero. This means that such a body is a two-dimensional, not a three-dimensional, object. Note that if we formally substitute any velocity greater than the speed of light into the formulas for changing the time interval, length, and mass, the time intervals, length, and mass will turn out to be imaginary quantities. This means that the formulas mentioned are meaningless at velocities greater than the speed of light. Part 8. The relativistic law of velocity addition. In classical physics, the choice of an inertial frame of reference is arbitrary. That is, instead of one inertial frame of reference, one can choose any other frame of reference moving relative to the first with any arbitrary, but, naturally, constant, velocity. This new frame of reference will also, naturally, be inertial. Then, the velocity of a body relative to the second frame of reference will be equal to the difference between its velocity relative to the first frame of reference and the velocity of the second frame of reference relative to the first. This transformation of a body's velocity, when moving from one frame of reference to another, is called the law of velocity addition. The arbitrariness in the choice of an inertial frame of reference also remains in relativistic mechanics. However, due to the relativistic change in time and coordinates, the velocity of a body relative to the second frame of reference will no longer be equal to the difference between the velocities specified above. The velocity of a body will depend on these velocities in a more complex manner. Moreover, the formula describing this dependence will also include the speed of light. The formula describing the transformation of a body's velocity when moving from one reference frame to another is called the relativistic law of velocity addition. The general rule is that the velocity of a body relative to the second reference frame will always be greater than the difference between the velocities of that body relative to the first reference frame and the velocity of the second frame relative to the first frame, that is, greater than the value of velocity in classical mechanics. And the greater the difference between the velocities of the first and second frames, and the greater the velocity of the body in the first frame, the greater the deviation of the body's velocity relative to the second frame from the classical value. Part 9. Constancy of the speed of light. In the special case where the velocity of a body is equal to the speed of light relative to the first frame, it follows from the formula for relativistic velocity addition that the velocity of the body relative to the second frame, regardless of frame's velocity, is also equal to the speed of light. This result is consistent with the experimentally established fact of the constancy of the speed of light. Thus, the speed of light in any frame of reference has the same value. It is for this reason that the speed of light has the status of a universal physical constant. It can be said that while all processes in a moving frame of reference slow down, the process of moving at a speed equal to the speed of light, in particular, the propagation of light, is an exception. This process is the only one that does not slow down.